All right, good morning, everyone. So, any questions about node voltage analysis? Homework submission completed. Okay. How about supernode? Anyone have questions about supernode? Or at least everybody understands supernode? Okay, let's tackle that and then I'll get into mesh current. So, node voltage analysis, the recap, we apply KCL to write our initial equation in terms of the branch currents, and then Ohm's law to express each branch current in terms of the resistor voltage. And then finally, we express each resistor voltage as the difference of the two node voltages. However, if we have, let's say, more than one voltage source in a circuit, if it's one voltage source, it's great. We can write an equation in terms of the two nodes at either end of the voltage sources. But if you have more than one voltage source and we need to write a KCL expression, we cannot, because the current for a voltage source cannot be expressed using Ohm's law. So what do we do? Well, what we do is this. We simply apply KVL at both ends of that source. So let's see. Just need to find the circuit diagram for the example. All right, this one. Where is... Okay, so we have the circuit that has more than one voltage source. Now, if you only have one voltage source in the circuit, then things are simpler. We simply choose one end of the voltage source as our reference point, and the other end, you automatically have an answer for that node voltage. But if you have a circuit like this, you could potentially choose this node at the bottom as your reference node. If we choose that as the reference node, then V3 is automatically minus 15. Right? Power supply positive is chosen as reference. That means the other end of the power supply, V3, is 15 volts below our reference point. Okay, so we automatically have eliminated two unknown nodes. Reference node is 0. And then V3 is minus 15. But now if we wish to apply KCL, what can we do? We can choose branch currents. So let's say this current flows right to left. This one's going up. This one's going down. And R3 or IR3 is going in this direction. Just some random assumptions based on those voltage sources. And then let's define, or let's note the current flowing through the 10 volt source as IS. Okay, IS. All right. So far, yes. No. Supernode is just supernode is not a. So the question being asked is that defined as a supernode, right? Is that the question? Oh, well, we're getting to that point. Yeah. So supernode is not a node that is defined as a supernode. It is simply an assumption. Okay. So it's just to aid our analysis. So ignore this for now. Okay? Ignore the word supernode for now. And let's say this is IR1, IR2, IR4, IR3. Okay. So let's apply KCL at node 1. If you apply KCL at node 1, what do we get? We have IR2 entering the node, and we have IR1 also entering the node, and IS leaving the node. That's our KCL based on our assumed current directions. Right? 2 currents entering, 1 leaving. Now, obviously, we can describe IR1 and IR2 using Ohm's law. And then we can describe it in terms of the node voltages. But we cannot do the same for IS. Or cannot apply Ohm's law. Right? We cannot apply Ohm's law to IS. So we need to find a way to eliminate IS. Okay, we need to find a way to eliminate IS. To do that, we'll apply KCL at node 2. If you apply KCL at node 2, what do we have? We have IS entering the node, and we have IR3 and IR4 leaving the node. Okay. So we have, in the first one, we have, again, IS is equal to IR2 plus IR1. Second one, we have IS is equal to IR3 plus IR4. And the same thing, we cannot express IS using Ohm's law. But what can we do if we combine both these equations? We remove IS. So if X equals A and X equals B, we can write A equals B. And that's all it is. From both the above equations, I can write IR1 plus IR2 equals IR3 plus IR4. That's all it is. A supernode, like voltage division and current division, is simply a shortcut. That is all it is. What we do is we draw a boundary around that voltage source, and we short out both these nodes together. So all of this becomes one single node, and you simply apply KCL to that entire node. So the name sounds fantastical, supernode, but it's nothing except a shortcut. All we are doing is we are skipping 2 steps. That's all it is. So we're just teaching the concept of supernode, but it can get tricky and confusing. So we don't need to do it. It just saves us some time if we do decide to do it. That's all it is. Again, supernode is nothing except a shortcut. That's all it is. And so we don't have to write these 2 equations. We can directly write this equation. Because if we take nodes 1 and 2 and we combine them, what can we get? Well, I mean, what do we get? I have R1 here, and I had my node 1 here. I remove the power supply and I'm shorting it to node 2. Everything else remains exactly as it is. Okay. And so this becomes the super node. Current directions that I assumed remain exactly the same. Everything else remains the same. The only difference is I don't have to worry about IS. So you write your KCL expression as it is. It's one single node. I have IR2. IR2 is entering the node. IR4 is leaving the node. IR3 is leaving the node. And so is IR1 entering the node. So I can directly write the KCL. That's all it is. Okay. So let's take a pause, think over that. Let me know if you have any questions. Yes. Or IR1. For IR1, it's V3 minus V1. Yes. That doesn't change. V1 and V2 are the same. Yeah. But you would still, no, V2 is still, so okay, I understand your question now. So the question being asked is, now that V1 and V2 are the same, does it change anything when I write my equations? The answer is yes and no. It just, well, actually the answer is no, it doesn't change anything. V2 still remains as it is. V1 remains exactly as it is. We don't change that. The supernode is just limited, or the concept of supernode is simply limited to this step. That is it. Do not extend it beyond writing that KCL expression. And so I always tell students, okay, we talk about supernode in class so that students are aware of what it is. But if you don't want to mess with it, then don't. Typically, if I'm solving a circuit, I don't mess with it. I just leave it as it is, and I write KCL expressions at both ends of that voltage source. And I just, it just takes a few seconds, 30 seconds of my time to do that. So I don't mess with the supernodes. I just write KCL expressions at both ends of the voltage source. Basically just doing this. That's, 2 extra KCL expressions. That's all it is. So it's a choice between writing this versus writing 2 more KCL equations. And that's all it is. And my preference is to not mess with the supernode. I just write the 2 extra equations. It still works out to be the same. Okay. Now, if you do want to practice and strengthen your grasp on the concept, and by all means, you can do both. Okay. I won't require a supernode application in any of my quizzes or exams. Okay, so I will have a problem where it says students must use node voltage analysis, but beyond that, you just show me how you know whether you apply the step-by-step analysis for node voltage, but nothing about supernode. Supernode will be optional. All right, any questions? All good? Okay, as I stated earlier, node voltage is this Monday, and then the Monday after that would be mesh current analysis. And so let's begin with the mesh current analysis topic. So in mesh current analysis, how many of you have already watched the videos on mesh current? Okay, let's start with questions. Do you all understand everything about mesh current analysis? Kind of similar to node voltage. Some students find it easier to use mesh current versus node voltage analysis. Okay, yes. Okay, all right, so we can talk about that, yes. So in mesh current analysis, if you watch the lecture video and you have reviewed the slides, we do the same thing as with node voltage, except we use KVL, apply KVL to generate our equations. That's EQN. So apply KVL to generate our equations. And then again, Ohm's law to express each voltage in that KVL expression as a function of the mesh current. Now, the most important thing that's we must remember is that mesh currents are not real. Mesh currents are hypothetical. They're purely theoretical. They do not exist in real life. And this is something, of course, you would have heard in the lecture video also, right? If it's a single branch, the mesh current is only, there's only one mesh current flowing through that branch. Straightforward, it's easy to apply KVL. You have the voltage, you simply express in terms of the mesh current. But when we have a shared branch, and the shared branch has two mesh currents flowing in there, then we must realize that the mesh currents are hypothetical. They are not real. Two currents cannot exist in the same branch of a circuit. It's just not possible. Okay. All right. So let's look up the homework problems and then we can get into the questions. How many of you have begun the homework? Mesh current homework? Okay. So a few. All right. E201. All right. Assignments. And then let's see. Let me bring the assignments up here. And then we have mesh current analysis. Okay, so we have three problems, 6, 5, 6, 6, 6, 7. One of them is pretty much similar to the one that we did earlier for node voltage. And actually, no, not in this one. Okay. All right, so which one did you have a question about? Which one? This one? 2.66? Okay. All right, so, well, let's, all right, R1 is 12, 27, R3. Let me bring this over on this side and copy it. Has someone already solved this? Anyone? Okay. Okay, so R1 is, let's see, what do I have at my end? 12 ohms. R2 is 27. R3 is 12. R4 is 30. R5 is 5. R6 is 6. It's been a while since I've solved this, so let's apply step by step. All right, question being asked is to find the value for V1 and V2. So I think part A asks for V2. Actually, no, V1 is not asked. Power delivered by the source. But let's find it anyway. Okay. So V1 is between R3 and R4, and we can see R3 and R4 are in parallel. So the first thing I would do is I would simply reduce that parallel combination into one resistance. And so what I will do is this. All right, so I got R1, R2, R3, R4 are combined, R5, oh, and this is R6. All right, so R3 in parallel with R4, I'm going to call this R7. R7 is the parallel combination of 3 and R4. What is the value for this parallel combination? Anyone? Get your calculators out, work this along as we, work with me as we go along. Sorry, how much? 8.57. Someone else, please confirm. Okay, great, 8.57. So now that we have reduced, what are we doing? What we are trying to do here is reduce the number of unknown variables. So in node voltage analysis, if you have a series connection of resistors, we'd combine them, reduce it so that one node is eliminated. And so here, if I chose to keep the original circuit as it is, I would have 1, 2, and 3 unknown meshes, meaning 3 unknown variables. By combining those two in parallel, we have eliminated one mesh. So now we are left with only 1 and 2. As with choosing a reference node, here we must choose a reference direction for our mesh currents, either flowing clockwise or counterclockwise. I typically always like to choose clockwise. And so if my current is going clockwise, I'm going to say IA and IB, going clockwise in both meshes. Okay. Now, because both mesh currents are going clockwise, now I'm going to mark out the polarity or the voltages that are caused due to this. So I'm going to say point of entry for IA is on the left. So plus on the left for R1, plus minus, plus minus. Again, similar to node voltage, this is a very important step. Do not skip this, because you must mark out the polarity that is caused due to these mesh currents. And once you have these polarities, now you can write out your KVL expression. Okay. So write the KVL expression for the first one. Everybody writes in their own preferred manner. I'm just going to write the way that is preferred by me. So I'm going to say, what is this? 12 volts. 12 VR1, VR7, VR7, VR6 is equal to 0. Minus 12 plus VR1 plus VR7 minus VR7 plus VR6 is equal to 0. The reason for the two VR7s is because R7 is a shared branch. We have two mesh currents flowing through there, I1, IA, and IB. Again, they're hypothetical. Because they're going the opposite direction, when we add up KVL, one of them will be added, the other one is subtracted. It's minus 12 plus, now we apply Ohm's law. So IA times R1 plus IA times R7 minus IB times R7 plus IA times R6 equals 0. And that's how you would write the expression. Let's take a pause while you write it down. Let me know if you have any questions. Any questions? Does everybody understand why we have two voltages in that same resistor and actually how to handle them? Yes. No. So the question being asked is why is it opposite? And is one of the reasons it's opposite, is it because we had a parallel combination and we reduced it? The answer is no. Anytime we have a shared branch, the shared branch will have two hypothetical mesh currents flowing through them. If we have two currents flowing through them, if both the currents are in the same direction, then instead of being plus and minus, you add both of them up. So if I had chosen, just hypothetically speaking, if IB, this is IA right now, and IB was flowing counterclockwise, right? But instead of flowing like this, if I had chosen IB to flow like this, then it would be plus IA R7 plus IB R7. So it's solely due to the choice of the mesh current direction. And similar to node voltage, it does not matter what we choose because it will balance out in the end. Because when we write the equation for mesh 2, this is for mesh 1. When we write the equation for mesh 2, both these currents would now be negative. And so the current direction that we choose does not matter. So does everybody understand the question and the response? Right? The plus and minus, sometimes that can get tricky. Okay. But again, it's a result of the choice we make for the current direction, mesh current direction. So if I write the equation for mesh 2, now in mesh 2, when I apply KVL, I have 3 voltages. So I'm going to write VR7. Again, VR7 is a shared branch. So two of them. And VR5 is equal to 0. First VR7 is positive. Second one's negative, positive, and positive. Then you apply Ohm's law. This would be IB times R7. So IB was negative in the first one. And now it's positive in the second one. And this would be IA times I7. And again, the signs are flipped, again, because we're writing KVL expression for mesh number 2. And that's it. Those are the two mesh equations. At this point, we plug in all the known values, constants, combine them to get linear equations, and we solve. Okay. Does that answer all of your questions about this problem? Okay. Let's just make one more point. If I had this coming like this, and if I was writing the equations now for mesh 2, these would be both negative, and so it would become minus IARA minus IBR7. You have a question? No. Okay, thanks. Random questions. Does that make sense for shared branches? Okay. Let's look at, does anyone want to look at any other problems? This one is straightforward because it has voltage sources. So we don't have to worry about anything because when you apply KVL, the voltage sources get added up. But if you have two current sources like these, so let me bring, this is problem number 2.67. So what do we do? It sometimes makes it easier if you have current sources. Because if we assume a mesh current that flows in the same direction as the current source, then we automatically have an answer for that mesh current, right? So if I choose, let's say, let's make this bigger. I have three meshes. There's no way to combine these three meshes without doing a major transformation. So if I choose a mesh current like this, and I choose another one like this. Now for the third one, I could go with a clockwise. If I go with a clockwise direction, IC will be minus 2 amps. But if I don't want to deal with a negative sign, I can just choose a counterclockwise direction, and IC will be plus 2 amps. Okay. So from these assumptions, I can write IA is 1 amp, IC is 2 amps. So the only unknown left in the circuit is IB, and that's it. Nothing else. So I write one equation in the middle, and we are done. Okay. IB is the only unknown. So write one equation for the middle mesh, mesh 2, and then we are done. How many of you have already solved this? Okay. Any issues? None. Okay. So if you have time, you can solve it right now if you wish. For those of you who have already done this, have you moved on to superposition? Okay. That would be the equation. IA and IC are already given to us, so we can reduce those. And the only unknown left would be IB in there. Everything else is known. Okay. Did anyone have any issues submitting the right answer? Okay. All right. We have a few minutes left. So yes, you have a question. Go ahead. Yes. So the question being asked is the reason it's both are positive is yes, because both are entering from the top. So for mesh number 2, both voltages are positive. Yeah. Got it? Okay. All right. Then let's look at the final concept of the super mesh. Super mesh, like super node, is simply a shortcut. And we use that when you have a current source in a shared branch and we can't write a KVL expression. So let's all right, so super mesh. Super mesh is again like a shortcut, but it's in fact even easier than a super node in a sense. So all we are doing is instead of applying KVL to a mesh, we apply KVL to a combined mesh, meaning just applying it to a loop. That's all it is. So in this example, we have mesh 1 and we have mesh 2. And if we apply KVL around this loop, we cannot, let me write this down. So since it's a KVL expression, we need the voltage across the current source. Okay. So all we do is we combine both meshes together. We apply KVL around this loop. The only thing to keep in mind is when you apply KVL, the mesh currents still remain the same. So you have I1 on the left and you have I2 on the right. Those remain the same. If I apply the combined KVL, I have I1 times 1 plus I1 times 2 plus I2 times 4 plus 10 is equal to 0. Let's see if I got it correct. I1 is positive. So 1 ohm is positive, 2 ohms is positive. I2 is entering from the left. So 4 ohms is also positive, and then 10 volts. Yeah. That's all you have to do. So super mesh is nothing but applying KVL to two combined meshes. It's basically just applying it to any electrical loop. Yes. Uh, good point. I took it a little bit too easy. Yes, the 2 ohms and the 4 ohms are in shared branches, so we cannot ignore those. Those must also be taken into account. Good catch. So this equation is incorrect. Let's rewrite this. We have minus I3 times 2, because I3 is flowing in the opposite direction. My KVL is going in the opposite direction. And then I have plus I2 times 4 and minus I3 times 3 and plus 10 is equal to 0. Now that is the correct equation. Now, if I did this and I handed in as my work, because my equation is incorrect right at the top, I would lose major points. Probably about 40 to 50% of my points would be gone. All right, again, shared branches, we must keep all both mesh currents in the equation. Okay. All right, does super mesh make sense? Okay. The concept is again similar to that. We apply KVL in x equals A and x equals B, so A equals B. But the implementation is far easier. We are simply applying KVL to that entire loop. The only thing to take care is we do not create a new mesh current for that loop. I1 stays as it is and I2 stays as it is. And then we just apply, and of course, shared branches, we must take those into account, right? Okay, we'll end class here today and we'll pick up here again. Well, not here. We'll pick up after this one. So superposition on Monday. Monday's quiz is node voltage. It's already there on the quiz schedule. Open book, open notes. Just apply the steps according to what we have learned, and you should be fine. You can apply node voltage to any circuit. Okay. All right. I'll bid you all a good weekend. I will see you all on Monday. Sure. So question asked is about the signs. So this is just me applying KVL. So when I apply KVL, what I do is I simply sum up the voltages according to their signs. So I just add up all the voltages and I equate it to 0. Most professors or some professors like to apply voltage source on one side and then the drop across each resistor. And that is also fine. We end up with the same equations. So I1 is going clockwise. So this is plus, this is minus, this is plus, this is minus. And I2 is again entering from the left. So this is plus, this is minus. For I3, this is plus and this is minus. This is plus, this is minus. So when I sum up my KVL in a clockwise direction, I have plus, plus, minus, plus, minus, and then of course plus. That's how I arrived at that equation. Now, students might be familiar with a different way of applying KVL, and it doesn't really matter how we apply KVL. We still end up with the same exact equation, no difference. So question being asked is about I2. So I2 is only in mesh 2. So it only flows to the 4 ohm resistor. It flows to that current source, but we don't really care about that. We can write one more expression. We can write, because 5 amps is shared between I1 and I2, I can write I2 plus 5 equals I1, or we can express it as a difference because I2 is in the same direction as 5 amps. So it's I2 minus I1 equals 5 amps. That's an extra additional equation we can write. But again, because it's a current source, we cannot add the voltage for that current source into our KVL expression. So we simply do not use it in our KVL expression. Which one? You're talking about I3? I3 appears here for the 2 ohm resistor and for the 4 ohm resistor. Oh, this is an error. That should be 4. That's why it probably generated too many errors. That was an error. So I3 times 4, yeah. Those two are combined only for the 4 ohm resistors. Yeah. Yes. Hold on. Let me